Let's do some notes about energy and work. Okay, so you've been making roller coasters, and we are going to start applying these ideas of energy and work with the roller coasters so that you can see what it could be used for. There are many uses for energy and work in the real world, but we're going to focus a lot of them on these roller coasters because you've been spending so much time making them. Now, I'm going to go through what these things are, how they're related to physics, how can we calculate things, and define some basic facts. So let's start with the word work. In everyday terms, work you would use in sentences like I'm going to work, or I'm going to be working out at the gym, or I have homework to do. And what it is implying is that it takes some effort. So work is something that requires some effort. This is our everyday use of the word work. In physics, it is similar to that definition, but a bit more concrete. So work is defined as a force applied over a distance. So if I am pushing a box across a floor and I'm pushing it really far, I'm going to be doing a lot of work. If I have to exert a lot of force to get it to go somewhere, then I'm also exerting a lot of force. If I'm exerting a lot of force and I'm pushing it really far, then I'm doing a crazy amount of work. The equation will look like this, in the most basic form. So work is force times a displacement, or distance. In a graph, if you plotted the force over different points on a certain path, then here's how you could calculate the work. You could find the area. So if you find the area for any shaped force versus displacement graph, you will find the work. Doesn't matter if it's curved like this. If you found the area underneath that curve, you would find the work done in this space. And sometimes it's easy, where if it's a straight line, you can just use geometry, since sometimes you can use calculus. If it was a curved, where you were given some function, then you could find the work by taking the integral. But we will do that later in the year. So the idea is the force applied over a distance, and it's a change in the total energy. We are going to define energy now so that we can understand what we mean by a change in total energy. And it's going to be a bit circular in my reasoning because energy and work are used to define each other. So, quick example of what work kind of would look like. Let's say my truck broke down and I have to push it to the gas station. I have to apply a force, and it's going to move in that direction, hopefully, if I exert enough force. I will be doing more work if I'm pushing it to a gas station that's very far away, or if the truck is really heavy and I have to exert a lot of force to get it to move. So if I push harder or farther, I'm going to do more work. Here are some facts. The units for work are a Newton times a meter. If you noticed, it's a force times a distance, so units will be Newton times a meter. And that is defined as a joule. So if you are talking about a real example of work, you would say, I did 10 joules of work. Now, here's energy. In everyday terms, you would use it in the following ways. I'm feeling energetic, I'm feeling hyper, quote unquote, or feeling tired. And, oops, let me go back. So, it's like your ability to do something. If you have a lot of energy, you could probably run a couple miles. If you are feeling exhausted and tired, you probably don't want to move very much. So in physics, it kind of makes sense with how that's defined. It's the ability to do work. So if you have a lot of energy, you can do a lot of work. And the units are also joules. So energy and work are very closely related. They're similar ideas, and we're going to compare and contrast and see how they are different, how they're similar. Energy is the ability to do work, and then work is a change in energy. So if I did work on a system, I changed its energy. If I have a lot of energy, I'm able to do a lot of work. So this is how they're related to each other. There are many, many types of energy, and here are an example of a few. There's heat energy. So if something is hot or cold, it'll have a certain amount of energy. Light has energy. Different types of radiation will give you different kinds of energy. So gamma rays, X-rays, infrared waves, ultraviolet waves all have different amounts of energy, but we will not be studying that right now. Sound has energy. So if you play an instrument, you know that anytime a sound occurs, something is vibrating. So something is moving back and forth to make a sound, and that is a form of energy. There is chemical energy. The food you eat has chemical energy, and your body uses that energy to help you do stuff, help you recover from a workout, to be able to be stronger and healthier. And the two that we want to look at a lot are those two, potential and kinetic energy. Now let's define what they are. Potential energy is the energy of position. If I put some really heavy object really high in the air on a surface, like right on the edge to where it could fall off, then you could say that that has a lot of potential to do damage if it fell. So if I put it even higher, it might have more potential to do some damage when it fell. So it's the energy of where something is, the energy of position. And it's defined like this. We've got U for representing potential energy, capital U. M and G is what you already know, mass and the acceleration of gravity. And then H is the height. So it's the distance it is away from something. So a common example is how high up something is. If you have a higher cliff that something is positioned on, you have a higher amount of potential energy. Kinetic energy is the energy of motion. So if something is moving faster, or if it's moving and it has a lot of mass, then it's got a lot of kinetic energy. So here are two equations. mgh, and we have 1/2 mv squared. So how is this useful? They are useful in the same way that the conservation of momentum is, but this time we're talking about the conservation of energy. So the total amount of energy before something happens is going to equal the total amount of energy after something happens. So the energy of a system will remain constant unless work is done on the system. Now, this sounds very similar to what we did with momentum. We said the momentum of a system will remain constant unless a force is acted on that system, an outside force. So in this case, energy remains the same unless work is done in order to change that energy. Here is an example. So here's the rock I was talking about, and it's sitting on the edge of a cliff. So it has a mass of 10 kilograms, and it is on a cliff that's only 14 meters. So what is the potential energy? We want to use our new equation, mgh. So we plug everything in, and we find out it has 1,400 joules. So very basic way to calculate potential energy. We'll do more complicated ones in a little bit. Here is a very basic calculation using kinetic energy. We have a car that's in motion. I want to know how much energy this has. So we use our equation that we learned, 1/2 mv squared, and we plug everything in. and we find that it has 5,000 joules. Let's see. Yeah, we have 5,000 joules. Alright, so two most basic ways to calculate kinetic and potential. Alright, so now we're going to use the idea of conservation, where we're going to use potential energy and kinetic energy together. And you will see why this can be very useful. So like we said, the total energy before will equal the total energy after. That's the big idea here. So if I add up all of the kinetic and potential energy at one point, then it will equal all the kinetic and potential energy at another point. So the initial energy equals the final energy. We're going to use an example of roller coaster. So I've got a couple of points that I could talk about. I'm going to talk about points A and points B, because you will see in some special cases this can make things incredibly simple. All I'm going to give you in this example is this. It starts 20 meters high, and it is also going to start with an initial velocity of 0, and that's at this point. So it's going to be released from rest at that point. So I gave you that the velocity at point A is 0, and it is 20 meters high when it's at 0. And our example, we are going to calculate the speed at B. And here's how we'll do it. So the energy at point A will equal the energy at point B. So at point A, now a lot of this will cancel out, but I'm going to show you the long way so that you see how this works. We're going to look at kinetic and potential. So at point A, we're going to figure out how much potential energy it has, how much kinetic energy it has. And that sum is going to equal the total energy at point B. Okay, so we're going to have a bunch of MGHs and a bunch of 1/2 MV squares. So try to pay attention to the subscripts so that we can know at what points we're talking about. So potential energy at A. So mg times the height at A plus 1/2 ma squared. So both of these points that I'm looking at, this is the height at point A, that's the speed at point A. Then we're going to do the same thing at point B. I'm going to add up the potential and kinetic at those 2 points. So here I'm going to plug in the height at point B. Here I'm going to plug in the speed at point B. Now, before we plug too many things in, because that's a very long equation, and we don't want it to get too messy, we're going to clean it up a little bit. If you notice, there is an m in every single term, so they will all cancel. So the fact that I told you nothing about the mass of this object, it does not matter, because they are all going to cancel. And we said that it's released from rest at point A, so that velocity is 0. And the height at B, it's all the way on the ground, so that's going to be 0. So those whole terms here are completely canceled out. So I'm going to rewrite this thing cleaner. And it looks like this. So g times the height at A equals 1/2 times the speed squared at point B. Now, we can calculate what the speed is very easily. It's just the square root of 2gh. And again, that's at point A. Alright, so if I plug everything in and then type it in my calculator, I now know the speed of that object at the bottom of the hill. Now notice that it is 20 meters per second and it was released from 20 meters high. Do not assume that's always the same. This is purely a coincidence. So different heights will give you different answers. So don't automatically assume, oh, it's 100 meters high, it's going to be 100 meters per second at the bottom. That's not going to always happen. So here's the takeaway. You can calculate different speeds given only heights. So in our case, we were only given the height at the first point and how fast it was moving there, and then we can calculate the speed at the very bottom. And then likewise, if you're given various speeds, you could calculate the height. And remember, we don't care what the path is. It doesn't matter that it went down a curved hill. It doesn't matter if it fell straight down. It doesn't matter if it went down a hill and went back up and then went all the way back down to a height of 0. They will have the same speed at the different heights. So that is the grand takeaway of how we can make this useful. All right, I'll see you back in class where we're going to apply this some more with the roller coasters and some more challenging problems.